All right, here we have a system of differential equations. We've got two equations and we have two functions, x and y. So just to note, x is some function of t and y is some function of t, right? So we have a third independent variable t, and then we have x and y are functions of t, and then we have two equations that relate x and y to the derivatives of x and y. All right, so we want to convert this into a matrix system. So we're going to convert this to a matrix equation, and we'll say we'll have a vector. We'll call it vector x prime, and that's going to be x prime, y prime, and a vector, right? And that's going to be equal to, we're just going to use our linear algebra method here. We're going to take the coefficients of this matrix multiplied by the vector that's the functions x and y. And of course, we could write it like this, where it's matrix A times just vector x. So we have this basic form of a system of differential equations. X prime equals ax. Okay. All right. So to solve these, we're going to take the matrix A and we're going to find the eigenvalues. And then we're going to find eigenvectors that go with those eigenvalues. And then we can put them into a standard form of the solution. So to find the eigenvalues of A, we need to find the determinant of A minus lambda I. Lambda is a constant. So just like you did in linear algebra, so you're going to subtract lambda from the main diagonal of A. Leave the other entries alone. And we'll take the determinant. So here, it's a 2 by 2, so it's going to be easy. So this is 1 minus lambda squared, and then minus 4. So let me multiply this out. So it's going to be 1 minus 2 lambda plus lambda squared minus 4. So I get lambda squared minus 2 lambda, and then 1 minus 4, that's minus 3. So you set this determinant equal to 0 and solve the equation for lambda. So we're looking for the lambdas that make this determinant 0. You can also think about it as we're looking for the constants that when we subtract those constants from the main diagonal, we get a matrix that has a determinant of 0, or we have a matrix where the columns are not linearly independent. There's a bunch of other things you could say. It makes A not invertible, right? So we're just looking for those values that when we subtract it from the main diagonal, it causes this to happen to A. So it looks like this one is going to factor pretty nicely. So I get lambda minus 3, lambda plus 1. That gives me two eigenvalues, 3 and negative 1. So for each eigenvalue, we're going to find eigenvectors. I said that was lambda 1, so we'll call this one lambda 2. Sorry about that. So let's say for lambda 1 equals 3, we need to solve this equation to get the eigenvectors. We're going to solve A minus lambda I x equals 0. We're just going to plug in this lambda. So it'll be A minus 3I times x equals 0. So this matrix is just A where we subtract 3 from the main diagonal. So we're going to just plug in 3 for these lambdas in our matrix A minus lambda I, and then we'll just augment that with the 0 vector and solve for x. So get 1 minus 3 and 1 minus 3 down the main diagonal. Augment this with 0 and row reduce. So I get -2, 2, and 2, -2. All right, so row reducing this is not very hard, right? So we can just add the 2 rows, makes the bottom rows zeros, and then we could divide the top row by -2, and we get 1, -1. And we need to, you could solve this in parametric vector form, or you could just solve it and, come up with an eigenvector. You just need one eigenvector. You don't have to find them all. But, we have a leading one there. That means this column corresponds to a variable that's free. So we'll say x1 is basic and x2 is free. So I'll solve for x1 in terms of x2. So x1 would be equal to x2. And then x2 is itself, and it's free. So it can be anything we like. So I want to come up with an eigenvector using these two components, and x2 is free. So if I let x2 be anything, I'll get an eigenvector. I can't let it be 0. We don't allow eigenvectors to be 0. But if I let x2 be 1, then I get the vector 1, 1. So we'll call this eigenvector 1 is 1, 1. And we just want to, do this process again with the other eigenvalue, which is -1. So for lambda 2 equals -1, we'll need to solve this equation. A minus -1 times I, so it's just going to be a plus I times x equals 0. So this means I'm going to add 1 to the main diagonal. So I get 1 plus 1 and 1 plus 1 on the main diagonal. That gives me 2's all the way around, right? Again, this is going to be easy to row reduce, subtract the 2 rows, divide the top row by 2, then we get 1, 1, 0, 0. So again, I have a leading 1 here. That means the second column tells me I have a free variable. So x1 is -x2, and x2 is free. So if I want to come up with a second eigenvector, I could use, say, -1, 1. If I let x2 be 1, the next one would be -1. So once you find your eigenvalues and eigenvectors, you can find the solution. So we called it x, and it's going to be c1 e to the lambda 1 t times the first eigenvector, the eigenvector that goes with eigenvalue 3. And then plus c2 times e to the negative t, that's for eigenvalue -1, with eigenvector -1, 1. And that is your solution. You could write it all together if you'd like. Let's do that. So if I multiply these inside, I get c1 e to the 3t, c1 e to the 3t. And same thing here. I'll get negative c2 e to the negative t and positive c2 e to the negative t. And then we add them together, we get this one vector. Remember, this represents the functions x of t and y of t. So that tells you what each function is, right? So x of t is c1 e to the 3t minus c2 e to the negative t. And y is c1 e to the negative, c1 e to the 3t plus c2 e to the negative t. And if we had an initial value, an initial vector, we would say then you could solve for those c's pretty easily as well.